Okay, let's get started. So this week we don't have a labs, so don't show up tomorrow or Friday. All right. Okay, so we are gonna basically continue. Before we do, I just want to make an announcement that homework has been posted. You should have received like an email, right? So it's due next Tuesday 5 p.m. Okay. Yeah. So and then for the submission, because I'm collecting homework from DL students, I encourage you guys to submit just on Sakai. Okay. So you guys can work on your tablet, or you guys work on just paper, just scan them and then convert that to PDF and then upload the PDF file on Sakai. Okay. Please don't upload like image files. Okay. Like just kind of JPEG or stuff like that. Yeah, please don't use those image files. Just convert that to PDF. You can do that using like smartphone apps, right? So yeah. All right. Okay. So and yeah, if you guys have any questions, feel free to stop by my office, or if you want to make sure that you see me, just send me an email for appointment. Okay. So yeah.
That just reminded me, quick question. For test taking in this class, is it going to be similar to 3002, where you're going to open up the test on Sakai for like a short period of time? Is it going to be like that?
Yes, it's going to be like that. Yes. Yeah.
Maybe weren't some of us in that class. What is your test like?
Yeah, so test like, so basically, I usually kind of open two options, right? For those who prefer to take in-person exam, I'll do that, okay? And then, like for actually most of students, they prefer to just kind of have a flexibility. So what that means is that I'm gonna just kind of post the exam on Sakai, for designated time period. For example, like over like 24 hours time period. But you can actually start anytime within the time period, but you are given only like 1 hour or 2 hours, the times that I set. So in the sense, like you guys can take home at home, you guys can take the exam at home, but like once you start, you have the given time, right? But you have a flexibility of starting anytime you like either morning time or dinner time, whatever. Does that make sense? Okay. Any other questions? So for this one, just again, just reiterating, we are going to have just one exam, okay? And the final exam is going to be a project, right? Okay, so let's continue on this photoelectric effect, okay? So let me just kind of recap the experimental setup, okay? So imagine we have a light source, okay? And then this light source, we can change the amplitude or intensity of the light, and also we have a way to change the wavelengths of the light. Okay, so for example, we can generate like green light, or we can generate red light, like etc. Okay, so this is a kind of, for convenience, we are kind of assuming we have capability that we can change intensity as well as wavelengths. Okay, separately, individually. Okay. And then with that, we are irradiating this light onto solid object, and then we are kind of observing whether photoelectrons are generated, okay? So if there is a sufficient energy to knock out electron out of solid object, we get photoelectrons, okay? So with this kind of a setup, we are actually doing some experiments, okay? And then just to recap, for general wave property, intensity of light, as we increase that, energy increases, okay? And then more specifically, energy is proportional to this amplitude square or intensity square. And then from experiment, what they found was that, for certain frequency, okay, for example, I'm gonna kind of draw here. Let's say this x-axis is intensity, and the y-axis is essentially kind of a, like yes or no, in the sense that photoelectron generated, okay? So electron generated for certain frequency, as they change the intensity, okay, as they increase the intensity, amplitude of light, the photoelectrons were never generated. Okay, so that was kind of a, like a very kind of puzzling, because, like if you look at just general wave property, energy is proportional to intensity, or, like amplitude square. Okay, so, like a, for any frequency of light, or for any, like a light source, as you increase intensity or amplitude, energy should be sufficient enough such that it can knock out the electron, right? But this is essentially kind of what it was observed. And also another case is essentially kind of, I'm going to draw again. And in this case, like because of this kind of like interesting phenomena, they did various experiments. In this case, they changed the frequency of the light source. Okay, they basically vary the wavelengths of the light, right? So F or nu. Okay, in this course, we are gonna change. We are gonna use this F or nu interchangeably for frequency, and then we do essentially kind of a plot the same way. Okay, yes, no, but here this one is essentially photoelectron generated, and in this case, as they change the frequency, okay, so below certain frequency, there was no photoelectron generated, but above certain threshold here, F naught, now photoelectron was generated. Okay, so in this case, okay, so in this case, obviously, intensity remains same. Okay. So for this experiment, it was kind of interesting again, because intensity was fixed. Okay, intensity was not changed, but as they increase the frequency, and after certain frequency, somehow photoelectron was generated. Okay, so this experiment showed that intensity was not really relevant, and what was important was frequency. Okay. So basically, this is essentially kind of what it shows here. Okay, so intensity high, even though intensity is high, if a low frequency of light was used, no photoelectron generated. And even though intensity was low, if you use a high frequency of light, it can generate a photoelectron. Okay, so that is essentially kind of a, observation or the interpretation of these two graphs. Okay. So this one was again, kind of an unsolved problem. And here, let me just kind of write down in this case here. Basically, classical prediction was that light intensity controls energy. Okay, that's an electromagnetic wave, right? Electromagnetic wave energy. And what that means is that any frequency of light or electromagnetic wave cause emission. Okay, meaning photoelectron generated. Okay, so this one was a classical prediction, but this is a photoelectric effect or photoelectric experiment. Okay, this is essentially experimental result. So this is a real data. Okay, real data shows that energy of photoelectron depends on frequency. not intensity. Okay, what matters was frequency, okay, not intensity. And also the photoelectron generated, or photoelectron, let me just write it here. Only above of threshold frequency. Okay, so this threshold frequency is essentially, this F naught, right? Only above threshold frequency photoelectron was generated. Okay. So again, scientists try to solve this mystery, right? And then here is essentially kind of where Albert Einstein contributed. Okay. So he explained this kind of a mystery, okay, by proposing light is made of discrete packets of energy. Okay? So this one was again kind of radical idea. Okay, light is made of discrete packets of energy, and then this energy, okay, discrete packet is essentially defined by this h nu or hf. Okay, nu and f is frequency. Okay, and h, again, this is Planck's constant. And then let me write down the value here. That is 4.136 times 10 to the negative 15 EVS, or 6.626 times 10 to the negative 34 joule second. Okay? So again, with this idea, he kind of basically hypothesized that energy transferred in packets. Okay. So here is probably you heard about the concept, okay, like a photon here. You probably heard about that. So here is where the definition kind of comes from. Okay, so photon is essentially massless particle, okay, of energy in electromagnetic wave. Okay, so here is kind of this concept particle comes into electromagnetic wave. Okay, so yeah, I'm going to talk about that a little bit here. Okay, so basically now look at this concept here. Okay, energy is now defined by what? Okay, this constant times frequency. Okay, this is why frequency kind of is a determining factor for energy of electromagnetic wave. Okay, so if you look at it, intensity is not involved, right, in this concept. What's involved is the frequency. Okay, so with this idea, look at this now. Okay, when you increase the frequency, now photoelectron generated, right? Why is that? Because now energy is transferred in packets of this massless particle, like photon. So now below that frequency, the energy is small, right? But now if frequency is higher than this threshold voltage, and then if that is actually above work function, now you can knock out electron from the object, and then photoelectrons will be generated. Okay. So with this idea, we can also explain as you increase intensity or decrease intensity, this one does not influence any photoelectron generations. Okay. So basically, with this idea, like he actually won, won Nobel Prize, okay, in 1921 for explaining photoelectron effect, okay, with this idea. Okay, so like he didn't win Nobel Prize because of a relativity theory. He won Nobel Prize because of explaining the photoelectron effect. Okay, and by the way, if you actually look at this equation, this one you saw it before, because look at this one now. Here, the Planck, right? Planck also came up with this idea, right? Energy of electromagnetic wave is essentially what? Multiples of this h nu or hv, right? So this is essentially what again? This is a photon, and this n has to be multiple, right? It has discrete energies, okay? So back then, it was just just using this concept and deriving this equation. But here, for Albert Einstein, he actually used the concept, to directly relate to experimental finding, and he actually made the concept much more solidified. Okay, so then since then, again, Planck's idea was also accepted, okay, in the field, and like now because of that, this Planck's law was used in describing like thermal radiation. Right. So, okay. So with that, now let us continue on this finding kinetic energy of photoelectron. Okay. So as we irradiate sufficiently high energy, electrons will be knocked out, and that is a photoelectron, and the kinetic energy of photoelectron is essentially given as this 1/2 MeV square, okay? And then this one must be equal to incoming energy of the light source minus work function, right? So basically, like here, let me just describe here. This h nu is essentially incoming energy, right? The energy of the incoming light, and then, like this energy must be higher than work function, right? Basically, binding energy, right, of the solid object, and then this difference, okay, h nu minus phi is essentially related to the kinetic energy of the photoelectron. And in this case, Me is the mass of electron, and that is 9.1094 times 10 to the negative 31th power kilogram. Okay, this mass of electron is obviously a very small value. Okay, so then with that you can easily find out kinetic energy, because h nu, this is essentially related to energy source or light source you're using, right? Which wavelengths do you use? And then phi is what? This is a material property, right? Work function is a property of the solid object. So with that, you can find out kinetic energy of photoelectron. Okay. Okay, so these are essentially like how new concepts describe or solve the mysteries that were lingering, in the classical physics. Okay, so again here, let me just again summarize that. Here we already know that light, we already know that light is electromagnetic wave. Okay, but with just this wave concept, Okay, with just wave concept, it cannot really describe photoelectric effect, because again, the energy is relevant to intensity if we just use just wave concept. Okay, but in order to explain this photoelectric effect, we have to introduce the particle concept. Okay, so here electromagnetic wave also has particle characteristic. That is essentially, photon concepts, right? Photon is a massless particles that is relevant to the frequency of the electromagnetic wave, right? So even here, we are kind of seeing, okay, even for electromagnetic wave, we are seeing wave particle duality. Okay, because if we just use a wave concept only, it cannot explain photoelectric effect. Okay, so we have to invoke some particle concepts to explain, the real phenomena. Okay. So again, electromagnetic is this wave particle duality, and then as we discussed earlier, the dual slit, right, double slit experiment here, electron. Okay, in this case again, we are essentially exhibiting wave particle duality. Okay, so this is essentially kind of what happens in modern physics or in small scale. Okay, so these are kind of three examples where classical physics kind of failed to explain experimental finding. Okay, but now we can describe with some like concepts of quantum mechanics. Okay, so up to this point, do you guys have any questions here? Okay, if not, we are gonna move on to the matter wave. Okay, so in this case, let us get into matter waves. Okay, this one is also an interesting concept because like here, let me just kind of explain. So matter, any matter is made of atoms. Okay, right? And then atoms obviously are made of neutrons and electrons and protons. Okay, so we are going to describe this atomic model later in more detail. Okay, but anyways, this is essentially kind of the fact we already know. And then here, de Broglie proposed that all particles or all matter or particle are associated with wave. Okay. This is a kind of like a more advanced kind of concept than wave particle duality. Okay. So it's what de Broglie suggested is all matters regardless of size. Okay, whether it's a small size or it's a bulk size or big size. All matter, all particles are associated with the wave characteristics. Okay? And then that wave length, okay, because this wave characteristic should have a wavelength, is defined by this h over p. Okay? H is Planck constant, and then p is the momentum of particle or matter. Okay, so it's simply mass times velocity. Okay, mass times velocity. It's just simple expression, and then this wavelength is called de Broglie wavelength. And then this one is suggesting that, like any particles, okay, like regardless of size, has wave characteristic. And then that is defined by h over p, okay? So then you might wonder, that is kind of interesting because, like big scale object like us or like a, tennis ball or soccer ball, we don't exhibit any wave-like behavior, right? Those are essentially kind of a particle-like. Do you agree? Right? But what de Broglie suggests here is, regardless of size, all matters, all particles should have wave characteristic, which is defined by this wavelengths. Okay? And it turns out, actually, we are going to kind of get into that, like a bulk scale object don't really exhibit wave-like behavior. Okay? I mean, obviously. And then, but how are we going to find out from this expression? Okay, so I'm going to kind of give you simple example here. Okay, so let us kind of apply this de Broglie wavelength to the bulk scale object. Okay, so in this case, macroscopic object. Okay, so in this case, I'm going to assume that this object has a mass of 1 kilogram, and let's say it moves 1 meter per second. Okay, so just kind of the realistic numbers for bulk scale object. And in this case, momentum is mv, right? That is essentially 1 kilogram meter per second. And now we are going to evaluate this lambda, de Broglie wavelengths. Okay, so that is h over p. And h is 6.6 times 10 to the negative 34th power joule times second. And then momentum is 1 kilogram meter per second. Okay, if you evaluate that, that is 6.6 times 10 to the negative 34 meter. Okay, so look at this number. Okay, this de Broglie wavelength. This has the number of that's 10 to the negative 34 power, right? This one is even much smaller than atom, right? Atom is do you remember what is the typical size of atom in terms of order? 10 to the negative 10, right? Like it's basically like a just below 1 nanometer, right? Like we say like kind of angstrom, right? Angstrom size. Angstrom is essentially 10 to the negative 10. Okay, so in the sense, this wavelength is much smaller than atom size, right? So for example, if I kind of roughly draw here, like I'm exaggerating here, this wavelength is so small, but this is essentially kind of atom, but atom is actually a lot bigger, right? A lot bigger. Like, so in this case, you cannot really see, wave-like behavior, right? Because wavelength is much smaller than atom, right? I mean, our bulk scale object is even larger than that, so you cannot really see any wave-like behavior. Okay, and also in addition to that, this one, even with the best available technology, we cannot even detect this wavelength. Okay, it's 10 to negative 34. Okay, so basically, because of this reason, we cannot see wave-like phenomena for macroscopic object. Okay, so this is why like a bulk scale object, ball or like a human being, when we collide with each other, we don't see interference. Okay, it's just kind of like bounced off, right? So de Broglie wavelengths, or this idea still holds, okay, because this wavelength, de Broglie wavelength, is much smaller than the scale of the interest, in this case, bulk scale object, right? But now, let us apply the small scale object. Okay, so another example here. is the electron. Okay. So electron from double slit experiment, what did we see? We saw wave-like behavior. Do you remember? From the double slit experiment, right? So let us use this electron as example for quantifying de Broglie wavelengths. So electron here, the mass of electron we already know that is 9.1 times 10 to the negative 31th power kilogram. And, you know, like the approximate, the velocity is essentially 10 to the 6 meter per second. Okay, 10 to the 6 power and meter per second. So then, you know, like we can evaluate this lambda, that is h over p, and then if we evaluate that 6.6 times 10 to the negative 34th power joule second, p, that is 9.1 times 10 to the negative 25 kilogram meter per second, and this one is roughly 0.7 times 10 to the negative 9th power meter. Okay. So now look at this value, right? This one is comparable to atom size, right? This one is like 7 angstroms, right? It's comparable to, you know, like a atom size. What that means is that now if we kind of roughly draw this wavelength, right? This wavelength here is now compared to the atom size, okay? So then it can behave like a wave. Okay? It can show actually wave-like phenomena, okay? So in the sense here, again, here, comparable to atom size, and then we can see wave-like phenomena. And indeed, we saw wave interference from the double slit experiment, right? When we were shooting electron through the double slit kind of a wall, we were seeing interference. Okay. So again, these de Broglie wavelengths kind of show you like why we are talking about wave-particle duality. Okay, so de Broglie kind of suggested, you know, for any matter, okay, doesn't matter, you know, like whether the size is big or small, every particle has wave characteristic, and then associated wavelength is defined by this h over p, okay, and then this wavelength is what we call de Broglie wavelengths, okay. So this again, you know, the reason why we don't see wave-like phenomena for bulk scale object, if we use this de Broglie wavelengths, it turns out the wavelengths turns out to be very, very small. Okay, so we don't see any wave-like behavior. But if we apply this de Broglie wavelengths for small objects like an electron, now de Broglie wavelengths is comparable to atom size, and we can start seeing wave-like behavior. Okay. All right. Okay, so, and then now let us kind of move on to the next concept here. Okay, we are gonna now get into the standing wave. Okay, this standing wave is actually a very important concept in quantum mechanics. So, you know, like there are two categories of a wave. First one is traveling wave. And then traveling wave is propagating, okay? So, and then traveling wave, let me kind of show you. This is essentially, let me see. Yeah, traveling waves is something like that, right? Basically, it's propagating in a kind of space here, right? It's essentially kind of a moving. It looks like a moving from one to the other side, right? And the standing wave. Let me just write here. And then standing wave. if you look at this one, so this one is a standing wave. Okay, if you see that, it kind of like a move. It kind of behaves like a wave, but it just kind of fluctuates up and down. It doesn't look like it's traveling, right? So it doesn't propagate, does not. Okay, just vibrating up and down in space, right? Just up and down. Up and down in space, okay, or in place, okay? So for this standing wave, we can also talk about some concepts here. Okay, so basically here, I'm gonna copy this one too. Just 1 second. Okay, so here, got it. So this one has a kind of feature here. If you, sorry, and this one is not really moving. Okay, so if you look at this black curve, okay, this one is essentially kind of a up and down, right? And then you kind of notice that at this point, okay, look at this point, the amplitude does not change, right? It stays at the 0 point. But if you look at this point, it goes maximum and then the minimum here, and then maximum and minimum, right? So this is essentially what we call node and antinode, okay? So this AN represents antinode, and then this 0 point is essentially called node, okay? So for this standing wave, there are several nodes and antinodes, okay? So the question here is, how to create standing wave. So if we want to create standing wave, what are the ways that we can do? How can we create standing wave? I mean, this kind of a figure kind of makes you probably confused. But the easiest way of creating standing wave is essentially fixing both ends, right? So for example, now this one is kind of misleading, but imagine the image is kind of chopped off here, okay, like here. Okay, when you kind of fix both ends, now at the end it's kind of a 0 point here and then 0 point, but inside it will fluctuate, right? So for example, if you kind of fix both ends of the string, and if you kind of give us some kind of a, the touch, it will vibrate, and then that is essentially standing wave. Does that make sense? Okay. So the first way of creating standing wave is to fix two end points, okay? And there is another way of creating standing wave that is essentially is given in this figure as well. So look at this one. Now look at this blue curve. So blue curve is the traveling wave moving to the right direction, right? And then if you look at this green curve, now green curve is a traveling wave moving to the opposite direction, right? and then it has the same amplitude, and it has the same frequency, okay? Same wavelengths. So in this sense, basically, when we kind of combine these two traveling waves in opposite direction, it can create standing wave as well, okay? So basically, second way is a superimposing two waves moving in opposite direction. Okay. So we are gonna now get into this standing wave. Okay. So like now, for example, consider a standing wave, and now we are creating standing wave between these two walls. Okay. So here, this is x equals 0, and then let's say this x equals d. Okay. So the spacing between these two walls is d, and then now let us think about what is the wavelength for the standing wave, and then the maximum wavelength that we can fit in this cavity or in this kind of spacing. What is the what is the maximum wavelength you can create while you are maintaining standing wave? So how can you create standing wave, and then like you are trying to maximize the wavelengths? So one possible way is obviously you are gonna fit one full wave, right? But there is another way that you can even increase more, okay? That is essentially you can make this way, right? Right. So basically now, like one full cycle is that, but just half cycle, you can actually fit the standing wave, okay? So what that means is that now this lambda, okay, this wavelength is essentially 2d, right? The wavelength of this standing wave, and then d is simply expressed as lambda over 2. And now let us consider the next longest wavelength, okay? That is obviously now you guys should know, and that is essentially one full wave, right? And then that is lambda equals d, and then d is lambda, okay? And then you can kind of go on, like the next one, let's say x equals 0, and here the next one, you are kind of fit 3. Yeah. Okay. So in this case, lambda is given as 2d over 3, or d is 3 over 2 lambda. Okay. But you can kind of keep going, then you will have many more standing waves that can fit into this cavity, right? And then you can find out how the lambda is expressed in terms of d, okay? So for that one, let us now kind of describe here. So if we generalize expression, this d is essentially n over 2 lambda. Okay, n is 1, 2, 3 integers. Okay, so for example, look at this one. This is lambda over 2, lambda 3 over 2, and then 2 lambda. It keeps going on. Okay, so we are just generalizing it. So we are expressing like that. Okay. Okay, so this one is a kind of just general concept for standing wave given the cavity, right? Given the cavity size. And then with this understanding, we are going to use electron in a cavity, okay? So consider an electron as a wave, and then now imagine we have cavity here, okay, and then now we are imposing some boundary. Okay, this is a potential energy. Okay, U is a potential energy, and then the distance between these two wall is D, and then we are putting electron inside here. Okay, so this one is essentially, like you can think of this as a kind of bucket with a, like infinite wall height. Okay, and then we drop the electron inside that bucket. Okay, and then obviously this one can kind of move from side to side, but now we are considering wave aspect. Okay, wave aspect of this electron. And this type of problem is called infinite potential 1D cavity. Okay, because we are talking about just in X domain. Okay, it's one dimensional, and then we are talking about this cavity or bucket with a infinite wall height. Okay. So with this assumption, let us now consider the wave amplitude of this electron outside of the wall. Okay, so like we can kind of consider this X domain, right? This is, let's say, X. Okay, X-axis, and the amplitude at the wall or outside of the wall must be 0, right? Because this is infinitely high wall, and amplitude or intensity of this electron wave must be 0 at the wall or outside. Okay, so in that sense, basically we kind of start with wave amplitude is 0 outside the cavity. Okay, and then what about this electron wave inside the cavity? How they look, for this electron wave inside the cavity? This is essentially same as the standing wave. Why is that? Because this wave amplitude is 0 outside the cavity or at the wall, right? We are essentially, like consider the wave, but at the wall, like at the 0 point and at x equals d, we are essentially fixing the amplitude to be 0. Does that make sense? So, imagine if there is any wave, okay? But because of this statement, wave amplitude is 0 outside the cavity, what does it mean? We are essentially fixing both ends to be the 0 point, right? We are essentially fixing both ends. And then we are essentially, like initiating any vibration inside the cavity, right? So it has to be same as standing wave. Does that make sense? Okay, let me just kind of get back to this one. Okay. So, just we are essentially assuming electron as a wave, right? We are considering this electron as wave, okay? So maybe this picture might be confusing, okay? So imagine electron is inside the cavity, and because of particle wave duality, we have a wave characteristic. Okay, so what that means is that now inside we are gonna form some waves, right? But here, it has infinitely high wall. What that means is that electron is not gonna be visible at the wall or outside the wall. Okay, so because of that, we are saying that wave amplitude is 0 outside the cavity. Okay, so what that means is that when we are really looking at just a wave kind of a shape at both ends or at both walls, amplitude is 0. Okay, and then while we are fixing both ends 0, any movement inside is gonna be essentially same as standing wave, right? Because we are essentially fixing the both ends, like as we kind of stated here. Okay, you are creating standing wave by fixing two endpoints. Okay, so and maybe I'll get back to this point next Monday. But for now, do you have any questions here?